Hi everyone, this is a pre-lecture video for the POGIL that will be starting on Wednesday, September 4th. That one will deal with the students' t-test, common statistical tests that we'll be using throughout the course. But before we get into that, I want to give you a little information about something that comes out of Harris 4.2, Chapter 4, Section 2, which deals with confidence intervals. But I'm also going to use this as an opportunity to sort of summarize all the different ways that we speak about dispersions, all the different ways that we describe the data dispersion. And what I mean by that is the sort of spread of data, which is what we commonly think of as error. This is your uncertainty. You know, we've seen it a lot as described as uncertainty. We've seen this in, let's say, your KHP lab, where you got 4 different concentrations for your sodium hydroxide concentration, and so what we use with a standard deviation to describe that dispersion, that uncertainty, in the values that you obtain for that. And there's actually a number of different ways that you will see, both in this class and in literature, if you follow this up and are doing some scientific research at some point. There's really no one or right or wrong way to do it. Each method has its own advantages and disadvantages, and they're, some are used more widely than others, but you will encounter them in different places throughout life. Alright, so this is what I'm talking about in terms of dispersion. We're talking about range and standard deviation, which are ones that you've probably seen before. In range, we're talking about pretty much that's the difference between your x, let's say this is one of your values, your minimum and your maximum. So this is not strictly a calculation, this is just, showing both the minor and major values of that. And we've seen that before in standard deviation. You guys have seen it a lot as well. Standard deviation, we're used to seeing this in terms of a sample set standard deviation. We're talking about S equals the sum of the squares of each of the difference between each of your individual values and the mean squared divided by n minus 1. So in this n, of course, is your total number of samples, and we take the square root of all that. Sorry about that. So hopefully y'all see that. We've seen this before, and you guys have calculated this already. So I just wanted to say that. So these are 2 real common forms you've already seen. And again, these are also ones that you've seen before. Relative standard deviation, that's just your standard deviation right down here. Standard deviation divided by your mean. Alright, and then percent relative standard deviation is the same thing, but you multiply it by 100, so this gives you a nice percentage. Alright, if you remember when we were talking about propagation of error, we talked about you need to use this percent relative standard deviation if you're doing a multiplication process or division process, which is times 100. Okay. Alright, so there's a couple other ones that we haven't talked about yet, and one of them is called the variance. So the variance is just your standard deviation squared. Okay. You may ask yourself why we might use variance, what the point of that is. If we already know what the standard deviation is, what would be the point of squaring it be? And if you think back to propagation of errors through addition and subtraction processes, you remember your total error would be, right, the square root of each of your individual errors squared, right, and summed. That's kind of small. But if you take the square of both of these, if you square both these sides, you get your total error squared equals the sum of each of your individual errors squared. And so lots of times you'll see this in terms of data tables. So if you're looking at a process that lots of times they'll be cataloged as having a variance, right, as opposed to a standard deviation, because the variances are more easily added to get the total. And so you can just imagine if you're trying to understand your process in a real quick way, it might be easier just to simply add up these variances as opposed to starting with a standard deviation. You have to square and then add up to get to your total. And this other one is called standard error of mean, and this one is really just your standard deviation divided by the square root of n minus 1. Alright, so this is your total number of samples. Alright, and this one is, I don't even know if this was even in your textbook, but it's used really widely. There's some debate of its value, but it's used widely, particularly in biology, a lot of biological texts. And this, lots of times, the reason why people use this is because they feel that it gives you a better idea of the confidence in your data because it's more dependent on the number of samples and our replicate measurements. And so the concept is that as you increase your number of measurements, it will give you more confidence in those values, and that this is used to represent that. So these are a couple of other common ones that you might find in literature that we haven't really spoken about yet. And finally, I want to talk about confidence intervals. So this one's sort of interesting because this ties in some of the concepts that we discussed during the discussion of Gaussian during our second POGIL assignment. And you'll see here this has a lot of things that you've seen before. This confidence interval here, sometimes just called CI. This is your mean values, of course. Your number of samples, which you've seen before, number of values, I guess I'll call that number of values. And then your standard deviation, which you've seen, which is just, right. And then it has this other value t. Let's call it standard depth. Okay. And t, this is something you haven't seen before. This is something that we're going to see a lot in this next week, where we're dealing with students' t-tests. Okay. And where this comes from is a table. Right, you'll find these tables of t values. You find these online, but these come out of your textbook. You see this table 4.2 here. Right? And what you see is different confidence levels. All right. And so what this does is this ties our Gaussian distribution here. If you remember when we talked about the sort of spread of possible values around a mean, would be dependent on that. In this case, they're talking about sigma, so we're talking about the standard deviation, okay, in terms of the population. And so if you recall, when we got to 2 sigma, this accounted for approximately 95% of all possible values between here and here, right? Of all probable values of a specific population based on a mean and standard deviation. And that came out of this formula here. And so what people have done is they've related this to the number of samples you have. This is a thing called the degrees of freedom. So degrees of freedom, should just call this DOF. Right? And this is the total number of values minus the number of sample sets. So in that example, if you recall from POGIL 2, we talked a lot about these car seat examples where you're measuring a bunch of cars, and the total of n, right? That's your total number of values that equal 218. And 218 all came from one sample set, so degrees of freedom for that was 218 minus 1. That would just be 217. Okay. You see that is much higher than this, but you can sort of see this value of t here changes, right? It approaches 2 approximately, right? Roughly 2 as you increase values. Alright, so I'm just going to go through a quick example of a calculation for that. So I want to show you this example. This is actually some real data that I had from some research when I was working with a group up in an institution called the National Institute of Standards and Technology. One of the things we were doing was trying to measure the formation of this biomarker here. This is called 8-hydroxyguanine. This is basically an oxidized base of a nucleic acid, and that this forms as a result of exposure to toxins, and it can be mutagenic, which cause DNA damage and other things like that. So here's 5 samples I got from one of my particular sets of experiments, and you can see we've got a range of values here, 1, 2, 3, 4, 5. This gives us an average, which is our x bar, and then our standard deviation, which is s. Okay. So if we go back and we think about this formula here, we just want to plug in those values here. Okay. And so if we look at this, plug in these values, we have, I'll just call this your confidence value. So wait, before we get started, what we're trying to find is a 95% confidence interval. Okay, so our confidence interval at 95%. All right, so we're going to start with our average value here, which is 5.50. Oops. All right, so x bar plus or minus TS over square root of n, right? So this is the same thing as that. Our confidence interval is x bar, right? So that's 5.50 plus or minus square root of n in this case, right? Our n is 5. And then our standard deviation is 2.51. Oops. But the one thing we have to figure out is what this t-value is. All right, and so if you look at this table, all right, what we need to figure out is how many degrees of freedom we have. And remember I said your degrees of freedom are the total number of values minus the number of sample sets. So in this case, it's just 5 minus 1, which equals 4. All right, so we go back to this table, and we want to find our 95% confidence level at 4. So we go back here, we say, all right, here's our degrees of freedom, 4, and our 95% confidence level is here, 2.776. Okay. So then we can just plug that in here, 2.776. Sorry, it's a little cramped. All right, and this gives us our value, which is 5.50 plus or minus 3.11. Okay, so what does that mean? So what that means is that that 95% of all of our values are going to be in between this range, and that range would be, since basically what we're saying is we're 95% confident that our actual population mu, right? So our actual mean here is between these ranges, so or it'll be between, what's that, 8.61 and 2.39, right? And so what that was just simply 5.50 plus 3.11 and minus 3.11. That gives us these values here, okay? But this here would be considered our 95% confidence interval, okay? And so, again, this is from Harris, chapter 4.2. So please review that before class on Wednesday. And yeah, I think that's it. So review that, and then we're going to move on to Harris 4.3 for our POGIL assignment. All right, have a good week.